Today we will be talking about imaginary and complex numbers. Our objective is to express the square root in terms of negative numbers and their products in terms of I. In the set of real numbers, negative numbers do not have square roots. An equation like x squared is equal to negative 1 has no solution. Imaginary numbers were invented so that negative numbers would have square roots and certain equations would have solutions. These numbers were devised using an imaginary unit named I and an agreement that I squared is equal to negative 1 or I is equal to the square root of negative 1. We assume that I acts like a real number in other respects. Square roots of all negative numbers can then be expressed as a product of I and a real number.
Start.
Definition. Imaginary numbers consist of all numbers, bi, where b is the real number and I is the imaginary unit, with the property that I squared is equal to negative 1. The first four powers of I establish an important pattern that should be memorized. Powers of I. I to the first power is equal to I squared is equal to negative 1, I cubed is equal to negative I, and I to the fourth power is equal to 1. Okay, now we will go through some examples. Our first example is the square root of negative 5 is equal to the square root of negative 1 times 5 equals the square root of negative 1 times the square root of 5, and our final answer is I square root of 5 or square root of 5i. Our second example is negative 1 square root negative 7 is equal to negative 1 square root of negative 1 times 7 equals to negative 1 square root of 1 times square root of 7, which finally gives us negative I square root of 7. And our final example is square root of negative 99 is equal to the square root of negative 1 times 9 times 11 is equal to I square root of 9 times square root of 11 is equal to 3i square root of 11. To multiply imaginary numbers or an imaginary number by a real number, it is important to first express the imaginary number in terms of I. Now we will look at some examples of imaginary numbers being multiplied. Our first example is 47i times 2 gives us 94i. Our second example, negative 1 square root of negative 3 times the square root of negative 7 equals negative I square root of 3 times I square root of 7. This equals negative 1 square root of 21, and our final answer is the square root of 21. Now let's look at complex numbers. Our objective is add or subtract complex numbers. To construct a complete number system, we shall define sums of real and imaginary numbers. We call these complex numbers. The definition of a complex number is complex number consists of all sums a plus bi, where a and b are real numbers and I is the imaginary unit. The real part is a and the imaginary part is bi. Every real number is a complex number because a is equal to a plus 0 times I. The complex numbers are an extension of the real number system. All imaginary numbers, bi, are also complex because bi is equal to 0 plus bi. We show these relationships with the following diagram: complex numbers, real numbers, and imaginary numbers. We assume that I acts like a real number, obeying the commutative, associative, and distributive properties. To add or subtract complex numbers, we can treat I as we would treat a variable. We combine like terms. Now let's look at some examples of complex numbers. Our first example is 7i plus 9i equals 7 plus 9 in parentheses I is equal to 16i. Our second example, 2 plus 3i in parentheses minus 4 plus 2i in parentheses is equal to 2 plus 3i minus 4 minus 2i, which gives us our final answer, minus 2 plus I. This concludes imaginary and complex numbers.